Hey everyone, welcome! Hi! Okay, now finally we get to learn about definite integrals. You remember, integrals and differentiation are two major units that we're doing, big units in calculus. So Riemann sum, and you'll see how that's related to definite integrals, okay? And how definite integrals are kind of different, same, but a little bit different than indefinite integrals, which has been what we've been doing so far, okay, until now. Okay, this chapter is kind of quick. I'm just going to go over a couple of main things, okay? All right, now, part one. Let's discuss areas of common geometric figures. And I'm going to give you guys a region, a sketch of a region that you should know how to find the area of. For example, I'm going to give you these three figures, okay? These are on these polygons that you know how to find the area of, more or less, right? I mean, this is a what? This is a rectangle, right? This is a trapezoid, and this is your classic circle, okay? So this is, I know this is cut off, but it just says 4 minus x squared, as you can guess, okay? So I want to know, do you know how to find the area of these without knowing this fancy Riemann sum or the definite integral? Yeah, so go ahead and try to find the area of these guys. Yeah, try to find the area, however you know how. Exactly, like a third grader would know that the area of a square or a rectangle is base times height, right? Yeah, so do it. And how about here? This guy would be, do you remember the area of a trapezoid? It's half, right, of the height, and you have two bases for trapezoid, right? Yeah. And a circle, you know that this guy is only half. Area of a circle is pi r squared, or in this case, it would be half pi r squared since we only have a semicircle, right? Okay, so that's what you did. And what did you get for the area? Did you get something like 2 times 4? So you got area equals 8. Did you get area is equal to maybe half times height was 3, 2 plus 5? For the circle, did you get half pi? And the radius was 2, so 2 squared. So did you get something like 2 pi? Yeah. So if you simplify this, you get 21 over 2, right? Yeah. So you know how to find the area of this. Well, you know what? Now you can do all this using integrals. You don't need to remember. Just in case you forget formulas, which you shouldn't, because these are pretty basic and classic ones. You can use definite integrals to do these too. Of course, not everything in life is actually a rectangle, a perfect trapezoid, or a perfect circle. So that's why integrals are much more beneficial in finding areas of real life things, okay? So we're going to do that. And the way you translate area into a definite integral is this. You're taking it from 1 to 3, right? You're taking this rectangle area from 1 to 3. So I have 1, the lower bound, upper bound. And then I have 4, because that's the equation from 4 to 0. So it's 4 minus 0, which is 4. You'll learn what I'm talking about with the y equals x line here, okay? So we'll do more of that, because you're right. We're taking the area perfectly above the 0. So that's why these work out like this, okay? Again, here, lower bound is 0, upper bound is 3, so it's 0 to 3, and this is your function, this function here, which we know how to write. Again, same thing, negative 2 to 2, right? Negative 2 to 2, and we have this semicircle here, and this is the equation for the semicircle here. And we put that equation here. And surprisingly, or not surprisingly, but cool, it's very cool that if you plug this integral into your calculator, a definite integral, earlier we were not using lower bound and upper bound. That's why it distinguishes itself from definite to indefinite integrals, okay? So when you plug this into the calculator, you're going to get 8, 21 over 2, and 2 pi. Woo! Cool, huh? So let's see how we can do that, okay? You have your formula sheet for integrals and derivatives, right? You know that colorful sheet that I gave you? So make sure you guys use that sheet, okay? So I'm going to discuss more with integrals, okay? Definite integrals again. Okay, sorry, this keeps getting cut off. So we have this. This is not a circle. This is not a sphere. It is some sort of function that's bound by this y equals x line, right? I'm sorry, y equals 0 line. So it's above the x-axis, okay? So what's the lower bound? Yep, you got it. I just swung my cap, so I'm going to grab it. Lower bound is 0, right? So you write the lower bound here, and you write the upper bound. But you're only looking at the x. You see how this is an x right here? So you won't get you only look at the 0 to x, like 0 to 4. You don't go this way because that's y, and we're going to learn how to do that later, okay? You're right. So I know some of you guys are like, why can't we go this way? You can. We're going to learn that later, but we always think of the easier way. In this case, this is much easier because it's going down this way from the 0, okay? So it's 4, and we write our function here, 4x, x squared. And this is our area, okay? All right, so again, the dx represents that it's going from left to right, the lower bound and the upper bound, okay? All right, let's move on. So I'm just going to give you some theorems that I need to clarify before we move on, just so that we follow the mathematical rules, okay? Continuity implies integrability. If a function f, I'm going to try to focus this a little bit better. Okay, if function f is continuous on a closed interval a to b, so a to b, then f is integrable on a, b, closed interval, and that's how we define that, okay? And that means it exists. As long as this is continuous and there's no gap, right? It is continuous and not discontinuous, then we can find the area under that surface. So integral basically means area, okay? All right, so it's the same really, okay? All right, let's move on to the next theorem that I'm going to show you. Okay, so it's just a definition, really, of an integral of an area of a region. Again, if you want to write this down, you can. You don't have to, as long as you understand these, okay? Theorem 5.5. The definite integral as the area of a region. If f is continuous on a non-negative on the closed interval AB, then the area of the region bounded by the graph of f, the x-axis as we were talking about earlier, right? And the vertical lines, these are the vertical lines. This is the x-axis. It's bounded by x equals a, x equals b. These are the vertical lines, and this is the area then, okay? We're going to do a lot with this. Most of you will be just doing the integrals using your rules, okay? So let's try what? Okay, let's try some, we're going to try now some part 2. We're going to be doing some properties, okay, using definite integrals for properties. When we get into 5.4 later, we're going to be doing more and more with definite integrals and actually applying the rules, okay? But for now, just the basics and its properties so you know what you can or you cannot do, okay? Evaluating basic definite integrals using theorems and properties, okay? Evaluate. Try to guess. So watch this. I went from pi to pi of sine x dx. So imagine your sine graph, right? Always imagine the function itself. Like you guys know all this, right? You've learned all this, okay? Imagine the sine graph, and I'm going from pi to pi. I went from pi to pi. So you know how a classic sine graph, it goes from 0 to 2 pi? So I meant here to here. But I went from here to here. So what do you think the integral is going to be? Don't just dump it into the calculator. What do you think? And you're right, it's 0. So we can conclude, okay? Upper and lower limits are equal, then we have no area. Therefore, the integral is 0. Try it on your calculator, okay? Try another case. Oh, shoot, I showed it to you. Think about how I can... Oh, well, okay. So how can I make these quantities equal? I have this integral here. I have this integral here. Do you see what's swapped? You're right, the lower and the upper, right? Lower and the upper, lower and the upper. So we're going from 3 to 0 versus 0 to 3. And I know that this area is negative 21 over 2, and it will talk about why area could be negative and so forth, okay? I want to make it equal. So how do I do that? Right? And you should have a picture of what this function is. You have 1, 2, and you have this graph from 0 to 3, 1, 2, 3, right? So you have something like this. So you have something like 0 to 3, and you're looking for the area here. Okay, that's what you should imagine, okay? Okay, but how can we make this equal if these are flipped? Any guesses? Okay, so to make it equal, we would have to put negative 3, negative here. And, you know, if you don't understand this quite yet, we're going to get better at this as we do in definite integrals, okay? We're going to show you how this makes all sense, okay? All right, so a couple of properties I want to show you so you can apply them yourself while you're doing definite integrals. That's what this section is all about. Now, 1, if f is defined at x equals a, then we integrate from a to a, f of x dx is 0, and that's what we showed the first example. Okay? If I'm speaking too fast, just slow yourself down when you're watching the video and take slower notes, okay? Second one is what we just defined earlier here. If f is integrable on a b closed interval, then we define integral of b to a of f of x dx is equal to negative of a to b of f of x dx. See? Because these are swapped, okay? And of course, it matters if b is greater or a is greater, okay? Okay, so in this case, it looks like b is greater and a is greater. That's why when we start with the greater number, we have to flip the signs, okay? Okay, so moving right along, okay? We're gonna practice all this, so don't panic, okay? Right, let's move on to the next, another theorem. These theorems come handy when you're actually doing your integration, okay? So that's why we need to define these theorems. And actually, this is the second to last thing, okay, that I'm going to show you today. So you're almost done, hang in there. Okay, so I have this integral here. Integral of a to b, right? I'm integrating from a to b. And I have this function here that I'm integrating, which is defining what this is doing, right? We have two vertical lines, it's continuous, so it's integrable, right? Okay, so I want to tell you a couple things. You see the c is just some point along this function, right? So if f is integrable on three closed intervals, okay? Three closed intervals, for example, a to c, c to b, okay? Three closed intervals determined by, as I showed you just now, a, b, and c. We can write it this way. Then, integral of a to b, f of x dx is what? How do I get from here to here if there's three different points three different points in between these functions, right? So all you do is you would say a to c, right? A to c first. And I know it's a little bit obvious. C to b, f of x dx. That's it. Sorry about this ugly c. Let's erase that, okay? So we're going to go like this, c to b. So again, it's kind of like segment addition postulate in geometry a little bit, okay? All right, let's try one. Find the area of y equals absolute value of x from -1 to 1 closed interval using integrals. And honestly, you don't need to know anything about integrals. Imagine this function. Imagine this function. What does this look like, right? Okay, so you're right. Like it does look like this. I know we know this because, you know, you've done it probably a ton of times. This is from 0 to 1, right? Because this is actually equal to plus or negative x, right? That's the absolute value. And these are the equations for it. So this is f of x of x. This one is f of x of negative x, correct? Okay, and we're going from -1 to 1. So what do you suppose the integral is, right? We're looking for this integral. We're looking for this area, right? We're looking for this place and from here. So we're looking for here to here. What do you think? Okay, write your guess. Stop the video and see if you can apply this formula here. Okay? Okay, so I assume you came back. Welcome. Okay? How about if I go from -1 to 0 and negative x dx? Right? This one is defined differently, right? But I'm going to add it to 0 to 1 of x dx. Now, who got this right? Woo! Give yourself a thumbs up! Thumbs up! Okay, great. And what do you, now if you get the next part right, then you're a real genius. So this is actually this, right? This whole thing is this. Well, what do you know about the area from here to here? Isn't this just a triangle? If this were a square, it'd be a 1 by 1. So what's the area of this area here? You're right, it's half. This guy here is also half. So your area is 1. Oops, sorry. Right? I'm sure you guys knew that because you're really just taking two triangles, right? You're taking two triangles and you're trying to find the area. Okay? And that's how you have to understand integrals as, okay? It'll make your life easier. I'm going to give you 2 more properties and that'll be it for this lesson. Hooray, you're almost done. All right, let's move on to the next part. I'm not going to show you too much. I'm going to share with you 2 properties, okay? Properties of definite integrals. If f and g are integrable on closed interval a to b and k is a constant, okay, then the functions kf and f plus or minus g are integrable and ab. So classic algebra things really, right? Because k is constant, okay? So again, if you have something like this where you are integrating from a to b and you have a constant k that you're multiplying the function to, you can pull the k out to make your life easier. Next one, if you have two different functions being added or subtracted from a to b, then you can separate them to make your life easier. So when you're trying to integrate, if you apply these properties, it'll make your lives much easier. Well, guys, let's try some, okay? So you're going to go back and now try this set in your textbooks right here. Can you try that for us? Okay, good luck. I miss you. Bye.